You all might have heard about imaginary numbers. Yes, the legendary I, where I square equals -1, and how it completely changed the way we look at equations. But what if I told you there's another number system out there, just as weird, but simply mind-blowing and almost no one talks about it? These are called dual numbers. And wait till the end, where I will show you how we can perform automatic differentiation using dual numbers almost effortlessly, without writing a single limit. See, we define complex numbers as a plus b times I, where a is the real part of this complex number and b times I is the imaginary part. In the same way, dual numbers are defined as a plus b times epsilon, where epsilon is a Greek letter and a completely different kind of quantity. Here's how we define it. Epsilon is not 0, yet epsilon squared is 0. That is, when you multiply epsilon with itself, it vanishes. Yes, that's it. I know it sounds crazy, but this tiny rule changes everything. Let's say we have two dual numbers. The first is a plus b times epsilon, and the second is c plus d times epsilon, where a, b, c, and d are real numbers. Similar to the case of complex numbers, for adding or subtracting two dual numbers, we simply add or subtract the corresponding parts, the real parts a and c, and the epsilon parts b and d. For multiplication, we multiply the terms just like we do with algebraic expressions, but with one key thing to remember: epsilon squared is 0. We get AC plus AD times epsilon plus BC times epsilon plus BD times epsilon square, which is 0. So we are left with this. Suppose we want to divide one dual number by another. Now, just like with complex numbers, we want to get rid of the epsilon from the denominator. So, we use the trick of multiplying both numerator and denominator by the conjugate of the denominator, which, in the case of dual numbers, is c minus d times epsilon. I will not bore you further, as it is super easy, and you can do it yourself. Now see the magic. Let's say we want to find the derivative of a function like f of x equals x, squared at the point where x equals 3. Normally, we'd use limits, rules, or formulas. We know its derivative will be 2 times x, and at x equals 3, f prime of x will be equal to 2 times 3, or 6. But with dual numbers, we can do it in just one step. We simply plug in the dual number 3 plus 1 times epsilon into the function, which means we evaluate f of 3 plus epsilon, which will be 3 plus epsilon whole square. Why 3 plus epsilon? Because we're evaluating the function at x equals 3, and that tiny epsilon carries the derivative information through the calculation automatically. Now, square this. We get 3 squared plus 2 times 3 times epsilon, or 6 epsilon, plus epsilon squared. That becomes 9 plus 6 times epsilon, because epsilon squared is 0. And here's the trick. The real part, 9, gives us the value of the function at 3, and the coefficient of epsilon, which is 6, directly gives us the derivative at that point. I am getting goosebumps right now. Yes, this is real. You are not seeing any dream. So without using limits, rules, or any differentiation formula, we got the answer instantly. Let us see why this magic works. For that, we will try to find a plus b epsilon to the power n. In order to find this, we use the binomial expansion, so a plus b epsilon whole raised to n becomes a raised to n plus n times a raised to n minus 1 times b epsilon plus n times n minus 1, divided by 2 factorial times a raised to n minus 2 times b squared epsilon squared, and so on. But since epsilon squared is 0, all terms that have epsilon squared or higher powers of epsilon become 0. So we are left only with the first 2 terms. That is these two terms. This is the beauty. The first part gives the value of the function at a, and the second part, which is the coefficient of epsilon, gives this which we all know is the derivative of the function at a times b, and therefore we set b equals 1. Now note that we define standard functions on dual numbers such that the real part gives the function value, and the epsilon part gives the derivative at that point, all in a single step. For example, we define sine of a plus b times epsilon equals the sine of a plus b times cos of a times epsilon. Similarly, we can define exponents, logarithms, or trigonometric functions. We are able to define them like this because of the Taylor series expansion of these functions. I will not go into the details, but you can trust me. Now we can also use dual numbers for multivalued functions like, suppose we have this complicated function which depends on both x and y. The partial derivative of this function with respect to x, which means we assume y as constant and differentiate f of xy only with respect to x. We will get this. Similarly, the partial derivative of this function with respect to y will be this. Now suppose we want to find the value of this function and both the partial derivatives at x equals pi and y equals pi. Then theoretically, on substituting both of them here, we get f as 0, f prime of y is also 0, and f prime of x is 1 over 1 minus pi square, which is nearly minus 0.113. Now here comes the magic. If we use x equals pi plus epsilon sub x, which means it is an epsilon of x, and y equals pi plus epsilon sub y, and substitute it in f. Note that both the epsilons follow these dual number rules. So after doing dual number operations on it, we get the real part as 0, the coefficient of epsilon sub x as 1 divided by 1 minus pi square, and the coefficient of epsilon sub y as 0. This means, in just one calculation, we got the value of the function and both the partial derivatives at once, using the magic of dual numbers. This is why dual numbers are used in automatic differentiation in machine learning frameworks, 3D computer graphics, and physics engines. They're fast, clean, and shockingly elegant. If you enjoyed this video, please don't forget to like, share, and subscribe to our channel. Also, you can support my channel by joining our community and becoming a member. So good.